First of all, let's try to find the limit as x approaches 1 of x to the third power minus 1 divided by x. Now, a limit, when you're trying to solve a limit problem, basically what it's asking you to do is as x approaches a certain value for a function, so in this case our function is this, so let me just write it down. As x approaches some value, right, for a certain function. So in this case our function is x to the third power minus 1 divided by x. Well, what's the y value going to approach? So the limit as x approaches a of f of x, well, this is going to be equal to some y value. So as x approaches a certain value for a function, well, what's the y value going to approach? And, we can look at this graphically. So that's one way to do it. So let's say if we have the function x to the third power minus 1, and then we're dividing this by x. So this is like the problem we're looking at. Notice, as x approaches 1, the y value approaches 0. So the limit as x approaches 1 of x to the third power minus 1 divided by x is just going to be equal to, well, 0. All right, because the y value approached 0 at that graph, and the graph as x approached 1. And if you were to solve this algebraically, well, all you would have to do is you would have to substitute 1 in for x. So in this case, if I have 1 to the third power, right, 1 to the third power minus 1 divided by 1. 1 minus 1 is just 0. 0 divided by 1 is 0. And that's how you would kind of do it algebraically. Now, let's say if I have the limit as x approaches 3 of, let's say, I don't know, x squared minus 9 divided by x minus 3. What do you think this would be? Now, kind of the first method we did for this problem, we looked at it from the graph. So that's one way to do it, right? We can look at the graph for the limit, for the function, to find the limit. And another way to do it, we did direct substitution. That's another way we did it. So to find a limit of a function, one way, another way to do it is you just plug in the value for x, and then, just see what the y value is at that point. However, if I try to do direct substitution for this limit, I'm going to get 3 squared minus 9. So 3 squared minus 9 is 0, divided by 3 minus 3, which is 0. And, anything divided by 0, can't divide by 0, right? So how the hell do we do this problem? Well, you're going to use a couple of your algebra skills, and you're going to realize that the numerator is a difference of squares. So difference of 2 squares. So it's going to be the limit as x approaches 3 of x minus 3 times x plus 3 divided by x minus 3. Okay? Notice how the x minus 3's, they cancel out. So you're just going to be left with the limit as x approaches 3 of x plus 3. And now we can directly substitute 3 in for x. So we just get 3 plus 3, which is equal to 6. Now, notice here. So if I were to graph out the function x squared minus 9 divided by, what was it, x minus 3. All right. Notice how as x approaches 3, the y value, right? Look at the y values. The y value is, if I could click on a point, the y value is this part over here. So look at the y value as I approach 3. Look at the y value as I approach 3. Look at it gets closer and closer to 6, right? So that means that the limit as x approaches 3 of this function is going to be 6. All right, so that's an important idea to know. An important idea to know is that even though, right, you can see here, the function itself is undefined at x is equal to 3, right? Because you can't plug in x is equal to 3. Otherwise, you're going to be dividing by 0. But the important thing to know is that when you're doing a limit problem like this, you're trying to look at the values that are around the point. So notice how if I go around my undefined point, well, my y value approaches 6, right? So even though the actual point itself is undefined, what I'm doing is I'm looking at the values around the point to see what the y value approach. So yeah, just kind of a summary of everything. Well, you could still have a limit for a function, even though the function itself at that point is undefined. So we can use this for another problem. what's the limit as x approaches 1 of x cubed minus 1 divided by x minus 1? You can factor out the numerator, because if we directly substitute in 1 for x, notice how we have 1 minus 1 in the denominator, which gives us 0, and we don't want that, so we can factor this. So to factor the numerator, you have to realize that this is a difference of cubes. This is kind of why like algebra 2 and algebra is important. It's because you're going to be using those skills in these types of problems. So make sure that you got your factoring skills all good. All right. So we have x. Actually, let me just use x and y. X to the third power minus y to the third power. It's going to be same. It's going to be same, opposite, and then always positive. So to memorize this, use something known as SOAP. So same sign, so same, opposite sign, and last sign is always positive. So same, opposite, always positive. That's how you remember how to factor this. So you are going to get this is going to be equal to the limit as x approaches 1 of, well, in this case, my x value is going to be x itself, and my y value is going to be 1, right? So it's going to be x minus 1 times x squared plus 1 times x, which is just x. And then this is going to be plus 1, and then divided by x minus 1. Now notice how the x minus 1s cancel out, so you get the limit as x approaches 1 of x squared plus x plus 1. Now that we don't have that nasty denominator, we can just plug in for the x values, right? Just do the substitution, and you get 3. And if you have a graphing calculator, it's good to check your work. But probably for, when you're doing like a test or something, you're probably not going to be given a graphing calculator. Otherwise, you just look at the graph the whole time. But for sake of the video, right, as x approaches 1, look at the y value. As x approaches 1, the y value approaches 3, even though 1 itself is undefined at that point. So there we go. Limit as x approaches 4 of the square root of x minus 2 divided by x minus 4. For this method, we're going to do something called multiplying by the conjugate. What we're going to do is, if you remember from, rationalizing the denominator, the conjugate is literally, right, our goal for multiplying by the conjugate is to get rid of our square root. So what we're going to do is we're going to multiply by literally our numerator, except the sign changes. So we're going to multiply the top and the bottom by the square root of x plus 2. So the exact same thing as the numerator, except the signs flip. Just to be a little clearer, let's just put parentheses. Because right now, what we got to do is we got to FOIL. So this right over here is going to be the limit as x approaches 4 of, and then let's start FOILing. Square root of x gives us x. Square root of x plus 2, and this minus 2 times square root of x, they cancel out. Remember, this is in the form of a minus b times a plus b, which we know when multiplied together is a difference of 2 squares. So we're just going to get a squared minus b squared. In this case, a squared, you'll notice how that's square root of x times square root of x. And minus b squared is just going to be 4 squared, so it's going to be x minus 4, right? Now for our denominator, we have x minus 4 times the square root of x plus 2. You might be saying, why am I not foiling on the denominator, right? I should foil on the denominator. That makes everything kind of simplified. Well, notice here, we have x plus 4 on the numerator and x minus 4 on numerator and the denominator. So we can cancel that out. All right, so limit problems when you're dealing with the conjugate is a little bit tricky sometimes, because sometimes what you do, in this case for the numerator, we're going to distribute because we want to get rid of the square root. But for the denominator, we don't distribute because notice here how x minus 4, x minus 4, they match up. So we're able to cancel them, right? So you got to be careful when you're doing these problems using the conjugate method, because sometimes, got to leave things in the factor form. So this is just going to be the limit as x approaches 4 of the square root of x. The square root of x plus 2, right? Plus 2. And then 1 over. So we can now that we dealt with the annoying denominator, we can now substitute 4 in. So this is just the square root of 4, which is 2. 2 plus 2 is 4. Answer is 1/4. Today we have the limit as x approaches 25 of x minus 5 divided by the square root of x minus 5. Now, in this case, if we directly substitute in 25 for x, we get the square root of 25, which is 5. 5 minus 5 is equal to 0. Can't have 0 in the denominator. So we're going to do the same method as before. We're going to multiply by the conjugate. In this case, we want to get rid of the square root, so it's going to be the square root of x plus 5, right? We're going to multiply the top and the bottom. Sorry. We're going to multiply the top and the bottom by the square root of x plus 5. This is going to lead us to, if we simplify the denominator, it's just going to be a difference of squares. So x minus 25. And for the top, well, you have, whoa, wait, what the hell? These two things don't match my denominator. What do I do now? Well, when it doesn't match the denominator, now it's time to FOIL, okay? So in the problem before, luckily it matched up with the denominator, so we were able to cancel out. But in this case, it didn't match, so let's just FOIL and see what happens. So we have the square root of x radical x. That's going to be 5x. That's going to be minus 5 square root of x. And then that's going to be minus 25. It turns out that you can actually try the hardest that you can to try to simplify this. It turns out that you can't really cancel anything out. So, I give up. I'll look at the graph of this. All right. So as x approaches 25, from the negative side, right? Because let's say we look at it from the negative side. So we're going from the negative side right over here, and we're looking at the limit from the negative side. Notice how as x approaches 25, if I can zoom out as much as possible. Notice how as x approaches 25, our y value just gets lower and lower and lower, all the way out to negative infinity, right? I can zoom out as far as possible. It's still going to go down. It's going to go down to negative infinity. So let me just write that down. So the mathematical way you would write this is the limit as x approaches 25 from the negative side. So we're looking at this from the negative side. So kind of from left to right, right? That's what we did in the graph for this function, the square root of x minus 5 divided by x minus 5, right? The limit for this is going to be negative infinity. All right, so that's what we're basically saying here. Now take a look at it from another perspective. Let's take a look at what happens as x approaches 25 from the positive side. So in this case, now we're going from the positive side, right? From the positive side, so right to left. And look at it. It's just going to get up and up and up. So as x approaches 25 from the positive side, what we notice is that, so let me just write this down. So the way you say it is the limit as x approaches 25 from the positive side. Well, take a look at what happens for this function. It's going to approach infinity. It's going to be infinity, right? It's going to approach infinity. Now, in order for a limit to exist, so in order for a limit to quote unquote exist, it has to approach the same value from the left to right side and the right to left side. So for example, right, for all of the problems we did, for all of the problems that we did, let's say we were looking at this one. So notice how as we approach 4 from the negative side, so basically from left to right, the negative side, well, take a look what happens. We get 1/4. Well, what happens as we approach 4 from the positive side, aka right to left? Well, guess what? It also approaches 1/4, right? So in order for a limit to exist, well, the limit from the negative sides, so the limit from left to right, basically, has to be the same as the limit as you're approaching that value from right to left, right? And in this case, notice how we have two different values. We have two different values for our limit, meaning that for this problem, the limit actually doesn't exist. So you would actually write that the limit does not exist, okay? That's how you would kind of say it. Let's say we want to find out the limit as x approaches negative infinity of 2 to the x power. How do we solve this limit? Well, let's just think about this limit intuitively, all right? So x is approaching negative infinity. So that means it's approaching a very negative value, right? A very negative value. Now, another way to do limits is you can actually just keep plugging in values for x and see what it approaches. So let's say if we have 2 to the x. Let's say if our x value is -1. 2 to the -1 power is 1/2. What about if our x value was -2? 2 to the -2 power is 1/4. What about 2 to the -3 power? Well, it's 1/8. So it seems like as our x value gets smaller and smaller, it becomes basically more and more negative, right? As our x value becomes more and more negative, right, our y value, or the result from that, becomes smaller. It becomes smaller and smaller, right? So that means that we can kind of say that the limit as x approaches negative infinity of 2 to the x, you can say this is equal to 0. Because if we plug in more and more negative numbers, right, -4, that's going to be equal to 1/16. Right, if we plug in, let's say, 2 to the -100, well, imagine how little this value would be, and imagine how little that value would be if we plug in negative infinity, right? Or like, -1, and it just goes on forever, right? Imagine how small this value would be. So at that point, even though the value itself isn't actually 0, so even though our value itself are not actually 0, well, we're approaching 0. So that's kind of the way to say it. Let's do some limit problems involving graphs. So right over here, I have the graph of f of x, which is this whole thing. I want you to find out the limit as x approaches -3 for this function, limit as x approaches 0 from the positive side, x approaches 0 from the negative side, and the limit as x approaches infinity for this function. Each tick mark on this graph represents change in 1. So this would be -1, this would be -2, -3, so on. And then this would be 1, 2, 3. This would be 1, 2, 3, -1, -2, -3. What's the limit as x approaches -3 of this function? Well, take a look. As x approaches -3, well, guess what happens? So as x approaches -3, well, the y value is approaching 0, right? The y value is 0 as the x value approaches -3. So the answer to this problem is 0. Even though the actual point itself is undefined, even though this point right over here is undefined, and the actual value for f of -3 is at -2. So let me just highlight this here. So even though the value itself is at -2, well, when you're looking at limit problems using a graph, you're only focusing on the surrounding points, okay? So as x approaches -3, well, in order to solve this problem, I would just have to look at the surrounding points. What are the surrounding points approaching? I'm not actually looking at the actual points itself. I'm looking at the surrounding points and seeing what they're approaching, okay? So remember, limit is what the y value is approaching, all right, from either side. The limit is not, it doesn't have to be the y value itself. So this y value itself is -2, right? The y value itself is at -2, but we're ignoring that, and we're only focusing on the points that are surrounding -3, right? So that's important to know. You're only looking at the points that surround what you're trying to find. The limit as x approaches 0 from the positive side. So as x approaches 0 from the positive side, so the positive side is this region. So as x approaches 0 from the positive side, we're approaching negative infinity. As x approaches 0 from the negative side, we're approaching positive infinity. Okay? So that means that if let's say I were to add another question, the limit as x approaches 0 of f of x. Well, the answer to this would be that it does not exist. Because the limit from, remember we said the limit from the left-hand side, the limit from the positive side doesn't match up the limit from the negative side, right? These two values don't match up, so therefore the actual limit itself for both sides don't exist. And the limit as x approaches infinity, well, take a look. As x approaches infinity, our y value slowly approaches 0. So 0 would be the answer for this one. So a function is continuous at a point, or the function itself is continuous if you can draw it without lifting your pencil. So what I mean by that is, let's say if I have a graph of f of x, and it looks something like this. Notice how I can draw f of x without actually having to kind of lift up my pencil, I should say. something like this. Notice how I can draw out the function without lifting my pencil. Function is continuous at a point if it's defined at that point. So there's a y value at that point. The limit as x approaches a of f of x does exist. And finally, this limit has to be equal to that point itself. So for example, let's say if I have the point 3, negative 2. Now we said how this function is continuous, right? So that means that if a function is continuous, that means that if we choose any point on the function, that point's going to be a continuous. Those points are going to be continuous, meaning that they're going to meet all of these criteria. And let me just kind of show you so you get like an understanding of this. So let's say if we have this point A, right? Now, f of A is defined at that point, right? F of A, we know that the y value is negative 2, right? When the x value is 3. So yeah, it is defined at that point. The limit as x approaches a of f of x does exist. Notice how as I approach a, so as I approach point A from either the left side or the right side, notice how it approaches the same value. So yeah, it does exist. And finally, the limit itself, right? We said how the limit itself, our limit right over here, approaches negative 2. So we said how this limit right over here is equal to negative 2, right? Because as our x value approaches 3, our y value goes to negative 2. And notice how that's equal to the actual point itself at that point. The actual y value itself at that point, right? F of a, the y value is equal to negative 2, and that's equal to the limit as x approaches that point. So that's basically kind of how a point is continuous, all right? So if a function is continuous at a point, it has to meet all 3 of these criteria. Now, in order for a function to not be continuous, well, there's kind of 4 scenarios. All right, so the first scenario, and I'm just going to write it up here. So these are examples when functions are not continuous. So the first scenario is when you have something known as a hole. So a hole. So when I draw out this function, a hole represents kind of a point where the function isn't defined. So for example, one example that we did for like a limit problem, I forgot what it was, but it was something like, I don't know, let's just say x minus 5 divided by x minus 4. Notice how if I plug in x is equal to 4 into the denominator, I get 0. So the function itself is not defined at that point, meaning that I actually have to lift up my pencil to then draw the other part of the function, right? So then it would not be continuous. So if a function is ever undefined at a certain point, well, it can't be continuous at that point. Because remember, one of our criteria is that f of a has to be defined. Another scenario when a function isn't continuous is when you have something like this. And this is normally seen with piecewise functions. Notice how I have to lift up my pencil, right? Now, if I wanted to draw out this function, I would have to lift up my pencil, which you saw before, right? So this function wouldn't be continuous. And right over here, this actually is something known as a jump, a sort of jump. So I'm just going to call it a jump. All right. So when you have a jump, then the function is not continuous. All right. Now, there's another scenario. Very similar to, one of some of the examples we did. But when we have a vertical asymptote, so basically, when a side approaches infinity and then the other side, approaches, negative infinity, right? So when so this is an example of a vertical asymptote. It's when, the function approaches plus or minus infinity, right? The function approaches plus or minus infinity. And, another example of a vertical asymptote, it can look something like this, right? Where it's like this, or it can be down here, So those are vertical asymptotes. I have to lift up my pencil to draw this. So yeah, this would not be continuous. This would not be a continuous function. And finally, actually, I'm going to use Desmos for this. But finally, we have something called an oscillatory kind of discontinuity. So all of these kind of scenarios we talked about where our function isn't continuous, they're called discontinuities. It's basically, right, something that does not make the function continuous. So a jump would not make the function continuous. This is a discontinuity where, vertical asymptotes, right? And you can have a discontinuity where a function is just not defined at that point itself, which is called a hold. The final discontinuity we're going to be talking about is the oscillatory kind of discontinuity. So it's when a function sort of oscillates infinitely fast. And take a look at this. Sine of 1 divided by x. Now, if I try to zoom in on what's happening on this graph, well, it's literally, the graph is literally going up and down. So the graph is literally oscillating between 1 and -1, kind of infinitely many times. Remember, a limit is just, when x approaches some number, what is the y value approaching? If our y value is just constantly going up and down in a certain value, well, you can't really have a limit there. So therefore, it's not going to be continuous. So I'm just going to write this down. So this is, I forgot how to kind of spell it, but I think this is how you spell it. So this is something known as oscillatory discontinuity. It's basically when this function goes up and down so many times that there's no limit at that point, which means that it's not continuous. Now, if we wanted a function to be continuous over an interval, so let's say this is the interval from, let's say this is a, and this is b. So we're selecting sort of some part of the function. If we wanted a function to be continuous from a to b, well, then all the points inside this interval have to be continuous.